I'm Brian, a software engineer.
And I'm Bruce, and we're here to talk to you about why things fail. This is a series where we talk about important historical failures, what happened, and what we can do about it. So, what's on the docket today, Brian?
Yeah, so we're going to discuss something called the bug herd round the world, which was the failure of the flight computer in the first flight of the space shuttle to properly boot.
Yeah, so this talk is not like last week, right? So, that was probably greed meets malfeasance that's motivated by greed. This is kind of the opposite of
Yeah.
that, right?
Yeah, so the Boston molasses flood is really rooted in the desire to make as much profit as quickly and as conveniently as possible. And today's issue, the bug herd around the world, is um, rooted in the difficulty that we have as a technical society in producing computer systems that function. So the space shuttle has as much money as is necessary to do the work that they're going to do, but still they introduce software bugs that end up delaying the first flight.
And you talk about the first flight. This isn't the first NASA flight, right? This is well into the
No,
program.
so this is not NASA's first flight. By this point, they'd already landed on the moon. Um, they had a space station. No, so this is the first flight of the space shuttle. So in the history um, of space flight, the capsule approach was seen as a temporary stepping stone to permanent and cheap reusable space planes. The early rocket pioneers really believed in the notion of space planes. You'll see in the 1930s, especially, almost everyone thinks that the future of space travel as a common and convenient thing for most of humanity is in the form of space planes, which makes sense. A lot of these people had seen aircraft, start from a rickety bicycle looking thing, transform in the space of a generation into a brand new mode of transportation. It turns out that space planes are actually very difficult to actually construct. They have a lot of things going against them, but because of this dream, the space shuttle was constructed, and it was pitched as being a pickup truck to the stars. The idea was that the space shuttle could fly a single space shuttle could fly several times a year. You'd get in economy of scale, all these sorts of things. Didn't work out like that in practice. There are some design compromises as a result of the Air Force's desire to use the space shuttle to potentially capture satellites, but ultimately a space plane is hard to pull off.
Yeah, and you talk about the word dream, and that kind of is a recurring, or it will be a recurring theme, because one of our suggested titles when we were talking about the series was against utopia, right? There's
Yeah.
always a dream in there somewhere in every single failure that we're going to talk about.
Yeah. So I think there is a hope for the utopian results of technology, that if we can just be clever enough, that if we can just be dedicated enough, we can overcome all limitations, um, which won't happen because of greed. In the case of the Boston molasses flood, you can't overcome the limitation of prohibition by just trying to crank through cane sugar as quickly as possible, which is a very meager utopian vision now that I think about it. Oh, but hello, Apollo. So this is Apollo, named for the spacecraft. If you look at the technological process, or progress rather, of the industrial revolution, it's hard to disagree if you put yourself in their shoes. That you would see human society radically change, and often for the better. If especially if, like most early space pioneers, you were from an upper class background. Of course, a lot of these early utopians are building military weapons to flatten people who are not from an upper class background. but that is one of the complications of the history of space flight. It's almost exclusively up until NASA starts working on the moon project. It's almost exclusively in the service of building ICBMs or medium range missiles. Even NASA's Apollo era, Mercury and Gemini are launched on ICBMs.
It's a capsule on an intercontinental ballistic missile, right?
Yeah, you either get a nuke or you get John Glenn. You can swap them out. What are the other?
Set us up. What's going on?
Every space shuttle flight has to go through a boot sequence or startup sequence. The idea being that you don't want to launch something that's not ready.
So the shuttle is on the launching pad, and we're starting to do some of the checklists that are that need to happen before we know that it's safe to put astronauts in, and then run through the countdown.
The shuttle has a pretty extensive startup sequence, as you might expect, for one of the more complicated machines that humanity's ever produced. And one of those steps is to boot the avionics system. So the shuttle is what we call a fly-by-wire craft, meaning that it's actually the computer that flies the space shuttle, and the astronauts fly the computer. So the computer sits as an intermediary between the actual hardware and the inputs of the human being. Most aircraft fly in this way now. Mechanical interconnects are really only common on smaller craft. So it's pretty vitally important that the avionics system function, and that it always function.
And what starts to go wrong at this point?
Right. So it turns out in the first flight of the space shuttle, of the entire program, the computer refuses to boot. It is not able to boot itself, and it refuses to start, delaying the shuttle flight.
We're not really talking about what we ran into last week, right? It's not that there was a lack of rigor in the way that this computer was constructed.
No. So the space shuttle, you can sort of argue without any concern, is one of the most correct software artifacts that humanity has ever produced. So every effort has been put into making this safe, resilient to failure, and correct the first time.
As they were working to make things correct, was there anything that they did to complicate the software?
At this point, I think we kind of need to talk about what the hardware of the avionics system is. So space is an unforgiving environment. You have no hope of rescue when you're in space. So if something breaks, it breaks for good, unless you carry a redundant copy of it, which is in fact what the space shuttle flight computer is. It's a multiply redundant set of hardware. There's actually two components in it. So when the space shuttle was first designed, the idea was that you would have in the primary avionics system, or the PAS, you would have 4 redundant, what they call general purpose computers, or GPCs. NASA sort of has this preference for acronyms, which makes it very hard to sort of get into research about NASA. So PAS, primary avionics computer; GPC, general purpose computer. The PAS are 4 identical GPCs, and the way these computers work is they all run the same software version. They're all connected to the same, what NASA called at the time, strings of hardware, which now we just call a bus. So you have hardware, which could be an engine, it could be a pressure sensor. All of these feed into the PAS, 4 PAS instances redundantly. Each one runs the exact same software, and they take the input and they run through their software program, and they produce an output. Each of these 4 computers vote. So they all check each other's result, And if they all agree, then the result goes forward. This is during the most complicated phases of flight where things really can't go wrong. During later phases of flight, each independent pass would be given substrings, so they would run different parts of the space shuttle in parts like power, because the GPCs were pretty power expensive. But during the most critical times of flight, takeoff, the pass is running in its fully redundant mode. The way the pass functions is they send synchronization codes to one another. So to do this voting, they have to agree on not even exactly what time it is. They have to agree on what CPU cycle it is. So they are periodically sending these synchronization codes back and forth to one another. The pass is what we now call a priority ordered real-time system. So every program that runs in the pass has a priority to it. So if you press a button to change the temperature in the cabin, that's a lower priority than orienting the main engine, right? So the pass has the ability to say, obviously these engine commands are higher priority, I will schedule these ahead of the others. And to keep this schedule, to keep the voting mechanism going, they send synchronization codes back and forth to one another. Works very well.
So Brian, you say it works pretty well. You mean that it works pretty well in isolation. And I bet that each independent software module has been tested pretty extensively.
They're tested pretty extensively. In fact, the review process for the software that goes into these things is pretty stringent. They have just a big book of all the software, the entire stack, and they go through in a group and they mark it. They mark up the whole thing whenever there's a new change that's introduced. And then each person in the room doing the review passes the book to the next person, and then they go through and they mark it independently. So this is to get across that the understanding of the people building this is that the software they're producing, the hardware that they're producing, is critical. That people will die in a very public way, in a way that might end the space program, which ultimately did. You know, we lost 2 shuttles and it destroyed the shuttle program. So the pass works very well. Unfortunately, NASA decided that the redundancy of the pass was not sufficient. So what they introduced sort of later in the program's development is what they call the backup flight system, or the BFS. So the backup flight system is also built on a general purpose computer, same hardware platform, but it is programmed by a separate group from the programmers of the pass. It's programmed to the same specification, but it is programmed in a completely different way. It's a synchronous, time-driven or time slice-driven real-time system, meaning that every program has a fixed amount of time that it's allowed to run, and it just runs through a fixed schedule. So on the one hand, you have a priority ordered system that has no fixed schedule, and on the other, you have a completely synchronous system. The purpose of the NASA's ultimate concern was, if you are needing to return, if there's been a catastrophic software failure in the past, if the group that built the pass let a bug slip through that means the pass can't synchronize, can't vote, just completely shuts itself down. NASA wanted that to be survivable.
They wanted that to be survivable. So their bet was that by building 2 completely independent systems, the probability that both will fail in exactly the same way must have been much lower.
Exactly. Yeah. So NASA is working off of a technique called inversion programming, which was pretty highly regarded in the 70s and the 80s. So the idea is that you build a formal specification of your program, and then you have independent groups programmed to that specification. The underlying assumption here is that bugs in software are independent of one another. So Bruce, if you and I work from the same specification, we will introduce bugs. Everyone will introduce bugs into their program. But the assumption of inversion programming is that, Bruce, because you are working in a different context than I am, your bugs will be different from mine. So that is the underlying assumption for the introduction of the BFS.
But is that true?
So it turns out that's not true. And a paper by Knight and Leveson in 1986 actually demonstrate that that's not the case. And it's a very, very clever paper. There was a missile detection problem that was pretty commonly used in the 80s for making experiments about software programming. What Knight and Leveson do is they give the specification for this missile program to a bunch of graduate students all across the country. And they ask them to program it. And they give them a set of acceptance tests, which was pretty common at the time for developing software from specification. And all of the programs that they got, or most of the programs that they got, I think, passed their acceptance tests. Additionally, what Knight and Leveson did was they randomly generated millions of test cases to run these programs through. And they found that in these randomly generated test cases, the programs had some systematic flaws. Through a neat statistical technique, they showed that these flaws were not independent of one another. They were actually a result of a common human bias in thinking about, in this case, geometry. So it turns out, because human cognition is basically the same across all of us, we all sort of systematically make the same mistakes. And later papers tried to invalidate Knight and Leveson's work, but they ended up accidentally demonstrating it again. So inversion programming is not something that you'll see done today. It hasn't really been done since the early 90s, but it's in vogue in the 70s and the 80s. So the assumption was, by introducing the BFS, you would still inevitably have software failures, but they would be independent of one another. They would not fail in the same way.
Sounds like a linear algebra technique that we're improving independent vectors in space or something like that.
Yeah, it's a statistical bet that was not validated, and it turns out that bet just didn't pay off.
Take us forward. So we know how the systems were created. So let's talk about how they actually failed.
It's important to understand that the pass and the BFS's role is to allow the shuttle to land safely. So it doesn't manage a lot of the same things that the pass does. It has a very limited ambition: land this thing. What it's supposed to do is take over entirely from the pass. That means that the BFS has to be ready to take over at a moment's notice. So it has to watch it has to accept the same string inputs. It has to accept the same data on the same buses that the pass does. Because the space shuttle is an older computer system, it has sort of like weirdo names for things. It has to accept the same inputs, and it has to watch the output of the pass. So it has to be aware of the pass's operation, which means that the BFS has to be synchronized with the pass. Now, if you'll recall, the pass is a fully asynchronous, priority-driven system. The BFS is completely synchronous. What this means is that there is a fundamental incompatibility in the way that the pass operates and the BFS operates. So it's easy from a high level in your specification to say that the pass and the BFS have to be synchronized. It's much more difficult in practice to actually achieve that because of their incompatibility in operation. So what the designers of the pass have to do is effectively add a hack to the pass. So time doesn't exist. Clocks exist, and this is especially apparent in computer systems, where there is no notion of time that you can orient yourself to. So the pass keeps track of the progress of the clock by counting the number of CPU cycles that have happened. So the GPC has a regular CPU cycle, And there's just a little counter that the computer knows how many CPU cycles have passed, and that is time to the pass.
So that sounds straightforward.
It is pretty straightforward. A lot of computers tell time that way. Or the challenge in any distributed network of computers, which is kind of ultimately what we're talking about here, is that time is very easy to tell, or time is very easy to create, I should say, in a single computer. But as soon as you have multiple computers that have to agree on what time it is, you have a real problem. So because the pass had to be synchronized, they have what's called a timer queue. And the timer queue is just a list of jobs that need to be done with their relative priority and how long that job is going to take. And every pass agrees about the timer queue because of the synchronization of the pass computers. So the way the designers of the pass decided to tell time was to read the first thing off of the timer queue and check when it needed to be done. And that time when it needed to be done was now. It's always a little bit into the future, but it's close enough to now that it's functional. So in that way, the pass is able to maintain its shared concept of now. The BFS doesn't participate in this. It's not synchronized on this timer queue because it has its own independent timer queue. So what they have to do to maintain the same concept of now is at boot time, the BFS has to read the passes now and maintain synchronization. The BFS is also designed to take over from the pass in the event that the pass catastrophically fails. So if the BFS detects that the pass is speaking nonsense, it ignores that nonsense. That means that the BFS has to agree with the data that's coming out of the pass, or it will refuse to synchronize. And in fact, that's what happened on the first boot of the STS-1 when it was on the launch pad.
The assumptions are starting to stack up, right? So the assumption that my time is the same as your time, the assumption that that we're correctly reading the idea of what nonsense is.
Yeah, they definitely are. And that's ultimately inevitable in an engineering project. You have to found every project on a set of hopefully shared assumptions among your engineering teams.
So I'm starting to hear some scary words, Brian. Hopefully, mostly, maybe, probably. You multiply those together often enough.
Often enough, goofy things happen. And the ultimate, the kind of the only thing that you can do when you're building safety critical software systems is to continue to mitigate risk. So how do you figure out your risk points, and how do you make the likelihood of their being expressed so low they will not be expressed in the lifetime of the technical artifact that you're building? So the idea would be that every nuclear reactor that needs active cooling will eventually lose the electricity to be actively cooled. How do you make the probability of that so small that it won't happen in the lifetime of the power plant? How do you make the likelihood of the pass suffering a catastrophic software bug in flight so low that it won't happen in the lifetime of the space shuttle?
So take us one step forward. Can we start to look at some of the architecture of the systems and drill into what was going on with this bug?
The issue here is after the BFS was introduced, so we talked about the timer queue earlier in the pass. So in the early days of the pass, the timer queue, there's a question. If you read time from the timer queue in the pass, what happens when you boot the computer? What's in there? Because if you're detecting now by what's at the top of this queue, if there's nothing in the queue, when is now? So what they decide in the early days is to fill the queue with a known set of nonsense. And the known set of nonsense is detected by the computer on boot, and it decides, okay, well, that clearly means 0. Later, after the introduction of the pass, they decide that they can improve the boot cycle of this computer by preloading known tasks that have to happen. And depending on when you start the pass, depending on what the cycle speed is, when it interacts with the first entry in the timer queue on this newly populated queue, it participates in what is called a cliff. So depending on one side of the cliff, it either rounds down or rounds up to find now. In, I think, 1 out of 81 times, it will round up. And as a result, now on the start for that particular start sequence is always one cycle into the future of where an independent computer, the BFS, would believe now is. And as a result, when the pass synchronizes for the first time with the BFS, the pass will tell the BFS that it is one cycle into the future, and the BFS will say, no, now is -1 from that. So what you're saying is nonsense, and I refuse to believe you, but because I am booting up, I'm not going to try and take over from you. I will just refuse to start. And then the whole thing sort of collapses because there is no agreement. So there's no way to safely start. Because in a critical software system, and this is something that Joe Armstrong points out in his research, if your software system enters a state that you didn't plan for, it enters a buggy state, you cannot trust that piece of software to then put itself back into a good state because it's already in some deviant internal order. Why would you believe that it could sort of push itself back into a good order? So the shuttle computer system refuses to start, which is a little embarrassing because the whole thing is stacked up. People are wanting to get into space. The eyes of the nation are on this thing, right? This is the very first flight of what is supposed to be the United States' future in space. The thing that will unlock space stations and the moon and Mars and all of that sort of stuff. And it sits there and the computer won't turn on. And the engineers that build the computer system are sort of fluxumed, right? Because they are a very, very professional organization, they've done a lot of integration testing of this thing. Sort of. It turns out
at least 50 times, right?
Yeah, it turns out it's actually very expensive to put it's very time expensive, I should say, because money is not an issue. Time is an issue. In any engineering project, there's always some resource that you're constrained on. And for the shuttle program, it's time. It turns out it's very time expensive in a lab to put a pass and a BFS together. So the integration testing would tend to turn the whole thing on and then do a bunch of integration testing. But this bug is only expressed if you keep cycling the on sequence, and it only happens 1 out of every 67 times. So you're very unlikely to see it in practice. It actually turns out that the way that they resolved this issue for the first space shuttle flight was just to reboot the computer. Once they understood the bug, once they were able to reproduce it in the lab, it was obvious that the bug could just be resolved by a quick reboot. Which they did exactly that, and the space shuttle flew successfully.
How long did it take to find the bug?
The first launch was intended to be April 10, and it took the engineers 2 days to find and diagnose the bug as trivially correctable with a reboot. So the actual launch was April 12. So two full days. 2 very stressful days, I can only imagine.
And then they called customer support. Customer support said, did you try turning it off and on again?
Customer support flew an entire crew of engineers out.
Injecting complexity for the sake of reliability is dangerous, right?
Right. Yeah, I think that for me is sort of one of the big takeaways from this. NASA late-ish in the design process inserted an entire new computer system that was sort of incompatible, which massively increased not only the initial build of the avionics system, but its long-term maintenance.
So Brian, let me see if I've got this right. So we have an organization committed to doing the right thing. We have a a bug that was essentially injected by adding complexity. In fact, we added a new system at the last minute. And the third idea is that we had some uncertainty that was kind of built into the assumptions that made the bug occur infrequently, but frequently enough. Did I get that right?
Yeah, yeah. I think for me, one of the key understandings that comes out of this is that resiliency, in introducing new components to a system to improve resiliency, is not free. Those components have their own failure modes, and they express failure modes in the existing system that you might not necessarily have thought through. So the BFS was added relatively late in the design process of the space shuttle, which you can sort of tell because it feels like a weirdo. It was assumed that the introduction of a completely independent software system with a completely independent mode of operation would improve the overall reliability of the space shuttle. But now, with the hindsight of history, even ignoring this bug, we're actually pretty sure it didn't. Not once did it ever actually find use in flight. We do know, however, that its introduction both delayed the first space shuttle flight, but it also increased the development cost in terms of money, which again, NASA didn't really care so much about that. What it did care about was time. So the introduction of the BFS massively increased the cost of developing this thing, but it also increased the ongoing maintenance of it. So for the rest of the lifetime of the space shuttle system, you had to maintain these two somewhat incompatible things. Introducing something late almost always has knock-on effects that you would not want. You're better off, unless you have detected a serious issue with your architecture, you're better off going forward with your original plan.
So Brian, let's catch our readers up. So this was almost a pretty good case study, not for things that were happening 20, 30 years ago, but now, right? So we're talking about distributed systems, which we have an increasing number of distributed systems. We have the idea of adding complexity. We have the idea of a lot of interfaces that are created, because let's face it, our web systems are now all integrated systems. In fact, a lot of our one-page apps are integrated distributed systems. So what can our listeners do to kind of guard themselves against these kinds of bugs?
Ultimately, I think the thing that you have to do to make yourself resilient to these types of issues is accept that failure is going to happen. Each one of your individual components has its own behavior that it will express, and some of those behaviors are failure modes. So your database will fall offline, it will lose a byte. This computer over here will turn off, this computer over here will turn on when you don't expect it to be on. And each one of these failure modes are sort of uncontrollable by you. So Charles Perrow calls this idea normal accidents. The idea being that these failures are not some sort of independent bugaboo. They are an essential component of an essential part of any technological artifact. And Perrow's argument is that if the failure mode of your thing is so dire that you actually can't live with it being expressed, then you shouldn't build the thing. Other sort of researchers argue that maybe that's okay, and that we should feel dread about our technical artifacts. So I think I definitely fall on the side of feeling dread about something is good because it makes you think through the implications of that thing, and how do you build observability into your thing? How do you detect that things have gone sideways? And I think a lot of Joe Armstrong's work was predicated around the notion that as soon as you can detect that something has gone sideways, you can kill it and restart it in a known good state.
I will also add the importance of mathematics and the importance of mathematical techniques to problem solving. So the work of John Hughes with the property-based testing and things like quick check is not becoming less important. It's becoming more important because the types of systems that we're building are increasing the reliance on things that are believed safe, but more and more likely to fail. And a couple of those are time, because we know that developers have this wild hubris with the idea of being able to get time and even date math right when it's an incredibly complicated problem. You multiply that when you go into distributed systems, but it's not just things like time. It's also things like floating point arithmetic, where what we're doing with today's machine learning and linear algebra techniques is we're taking huge matrices and we're expecting a certain amount of precision that just doesn't exist when you multiply them together, tens of thousands of times and in tables that are that large. So the models for math are becoming more important, but that's not widely recognized yet. And so as we rely more and more on things that are less understood, like machine learning systems and recognizers and things like that, we can expect to see those things fail so that it becomes important to describe a system mathematically in terms not just of whether something is correct or incorrect, but also tolerances and things like that. And we see this across elections, across prediction models, and all the way through the space that we're living in 2020.
I think one of the interesting things for me is we understand now that in highly studied software systems, in safety critical software systems, generally speaking, issues with the software don't happen as a result of programmer bugs. They happen as a result of specification bugs. So what you'll find is that the specification was incomplete in some way, and the software system itself was accurately carrying out that incomplete specification. Now, a lot of times, for most of us, we are not programming to a highly debated specification. We're programming to a project manager's vague notion about what's wanted.
Right.
And I think you're absolutely right. We have a bias toward our own technological artifacts. We want the things that we have built to be functional, and we want them to be good seeming, because in some sense they are a demonstration of our prowess as engineers, which is problematic when we go to select test cases, because of this bias, we tend to select test cases that demonstrate our prowess as engineers. So we find the happy path in our software. We need to emotionally. Random testing, on the other hand, does not care about our prowess as software engineers. And what it does is it helps explore the state space of our software. So you mentioned floating points. Floating points are completely accurate as floating point numbers. They're not accurate as math numbers. So they have these weird edge cases in, how the mantissa shifts up and down in terms of accuracy, that you can explore with randomized methods. Now, there's issues in exploring with randomized methods because how long do you run it, et cetera. But it is a marked improvement over listing out specific test cases.
It's harder to find the edge cases.
It's very hard to find edge cases. Exactly. If it had been more feasible to stand up the shuttle integration test rig and flip it on and off randomly, which is something that a property test for a distributed system should do. What does it look like when we flip this thing on and off rapidly? One thing I like when I work with doing, say, property-based testing or chaos engineering or anything like that, resiliency engineering in general, is a good invariant that I am inspired to by this particular bug is, does this software system boot? It's a nice, convenient little invariant to check that you will almost always forget to check because, of course, it boots. I turned it on once. Why would there be anything different in there? But our software stacks, even if we sort of cut out like the web and all of that, which I am very ignorant of, the software stack of just a single computer is huge. It's multiple millions of man hours of effort to just get a modern computer to turn on and get to a Unix user land. Very, very complicated. And that's just how technological civilizations go. They just keep, we just keep building on top of the layers of the past.
I strongly agree. And I also believe that our notions, that one notion of failure isn't enough, right? So we need first the Joe Armstrong mindset to handle failure in a first-class way. We need the John Hughes mindset to model our tests in a way that we can catch failures, and we also need the Pony style, the Julia style, where we can mathematically start to prove the correctness of systems, and all three of those things are going to be incredibly important moving forward.
What I really look forward to is a generation or two from now, people looking at the sort of tools and methods that we use today and being appalled at how primitive they are. Hopefully introducing more of these more convenient proof systems, and that was really one of the goals of ADA, right? The idea that you could introduce these formal checks for these highly safety critical systems, which kind of just didn't pan out, in part because of the complexity of building the compiler. It is something that we will have to continue to struggle toward. But yeah, we have to have a multi-pronged approach here, because even in a software culture where correctness was the most paramount thing, you get a boot bug because you didn't boot the dumb thing enough times to detect that there was actually a bug sitting there.
How do you detect it in the first place? How do you recover once that happens? And how do you build systems such that these things don't happen again? And all three of those are important.
Yeah, all three of those are important. And I think an additional takeaway that I would add is failure is inevitable. Every system that we construct in its behaviors that are expressible include things that we would prefer not to happen. And we just have to accept that and sort of plan for what are the worst cases and can we accept them.
So that's a wonderful place to wrap up. What's on the docket for next time?
Next time, we're going to talk about one of my favorite man-made ecological disasters, the Dust Bowl. There's a lot going on in the Dust Bowl. So I look forward to talking about that.
This is Bruce.
And I'm Brian.
For Why Things Fail. Take care, everybody.